last couple of years, we've made it stick a little better. But all spacecraft have that kind of stuff in just different geometries. So if you've put together your rocket, and you've got the engines and the tanks, and you've got the propellant, and you've built this little spacecraft, and let's say that this is my Soyuz spacecraft here, and I've got the tanks and the insulation and the engines are all the green stuff, and I fill it with propellant, and that's my mission. And I start launching a lot of these things to go do science in space, and after a while, I start realizing that I got an awful lot of tankage and insulation and engines in this business and not much mass getting there. And that if I were to build bigger, the way I build 747s and oil tankers and things, I could build one big system and all that stuff I took out of the middle would turn into payload. And so there's a real economy of scale that we do in going to orbit that you can see in the size of the big cargo boosters that they put together. This is a Russian Proton rocket. It's 4.5 meters across here, about the diameter of our payload bay. Ironically enough, the exact diameter of a Russian spy satellite is exactly the diameter of the orbiter cargo bay. Just go figure that. Here's one wheel of the train carrying it. Excuse me, there's one wheel of the train. There's the other wheel of the train. That's the train track. Give you a sense of the scale. Here's somebody my height projected from the foreground up next to it. He could stand here in the engine bell. And you can see the problem of delivering this, the 3,000 kilometers from Moscow, same problem we have getting our external tank around, or those 12-foot wide solid rocket motors. We have an issue trying to get them where they need to be. Imagine the bridges that this has to go under on that 3,000 kilometers of train track. Imagine clearing all of the sidings and all the oncoming traffic for half the width of the Eurasian continent to get this thing to the pad. It's a logistics nightmare to try to move this stuff around. Then figure out if you made it bigger, look at these welds in here. And even with perfect aluminum, it gets to be harder and harder and harder to make a structure that's going to hold together, bigger than the Statue of Liberty, and have that hold together as it feels several times the force of gravity. So if those welds aren't perfect, and I start making them thicker and thicker to handle a bigger and bigger rocket, I run into trouble. So just about at the edge of material strength. By the way, the Saturn was bigger because it used structural steel, right? Think about it. The orbiter weighs more than the S-4B stage. And so a rocket half the size of the Saturn V is delivering more mass to orbit now than we did in the Apollo era. Why did we build it out of structural steel and build it so big? Because we were on a race and we had to do it quickly and we didn't know any better. So we built the monster that you see on its side out there, and it costs like 11 times as much as an orbiter to launch one. So we make them lighter, we make them out of aluminum. There's the Proton carrying the first piece of the International Space Station, the FGV Zarya up there. Our tanks, same, almost exact scale. We build them a little bit wider. This holds 8 Olympic swimming pools of high explosive propellant, hydrogen down here, oxygen up here. There's a girder that goes between where the solid rocket motors attach, carries all the load. The shuttle, if you look at the nose where it attaches up there, that also transmits load up to that girder. And then the oxygen is the heavy part, and we carry it down the pipe, and we try not to carry any more oxygen than we absolutely need. Remember that sliding scale of how tight we hold the margins? When we burn out a tank and jettison it, we have drained the oxygen from this tank, we have drained it through that pipe, and we have my height of that pipe filled with oxygen. We have less than 1 second to burn those engines before they run out. If you burn out the engines with no fuel in them, they will explode. So you want to keep that as tight as you can possibly get and not carry anything more than you need because you lose payload weight. But doing the paperwork to keep the balance in there is really, really tight. And of course, we have to line it with foam to keep water from forming, the ice. And so there's a balance as to how much foam you put on versus how much ice you expect. We used to be able to get a much lighter foam on it before Freon 12 was outlawed. We put Freon 12 into the polyurethane and let it expand, and they took it away from us, and so now the foam is denser and we have to put more on. We then went and took aluminum and reinvented it with Alcoa. We now have lithium in the aluminum, and lithium is a very brittle metal, but it makes it ultra, ultra lightweight. And so we took, I think, what did we take out of here? 3,800 pounds out of this thing? 8,000 pounds, that's right. We took 8,000 pounds out of the tank. That's an awful lot of cargo, considering that the payload weight to orbit is about 20 tons. If we take 8,000 pounds, we took 4 tons out of the tank, which goes into payload. That was a big investment. Thank you for that. I was looking for that number. And now that they have it, they had to develop the stir welding technique to try and get the welds smooth. It's a very, very brittle material. Had to reinvent the machining techniques, but that's had huge payoffs in rocket technology since. So here you can probably spot some of your friends building this shuttle. Remember that this didn't exist when we were kids, right? There's one. Here's some of the people that thought this up and work on it every day. And what's really amazing is that this and everything that we do is going on inside something smaller than a pixel on this page, which is your brain. Do this exercise with me. Put your left hand on your head and make a mold of your head like a baseball cap. I love the view from here. You should see this. Use that mold to mold your right hand. Okay, so your right hand should now be the shape of your hair, your scalp, your skull. You go on inside the fingers, you've got your pia mater, your dura mater on the inside of the skull. And so now if you mold your left hand again, this little thing about the size of a grapefruit is all you've got to work with, okay? This is the size of the human brain. It is the same brain that we have had for over 5,000 years. There's been almost no genetic mutation of humans. We are 1/10 of 1% different from each other around the planet. What distinguishes societies from each other is their inventiveness, the knowledge that we teach our kids and pack into each new, fresh brain. If we just get new kids with a brand new open pattern to fill, and we teach them the best thing we understand. So we've learned out of the shuttle, and we're going to build better in the next generation. And there was nothing like the shuttle before. We've built on the shoulders of giants. And what's really amazing when you go back to that picture of Stonehenge is to see just how rapidly it's all coming together, and what a privileged life we live here to be able to do this. We are making history every single day with stuff that's smaller than those pixels, and it's all being done by the people in this room and our fellow engineers around the planet. The world has come together on the idea of the conquest of space. So we have tried to go to space with the biggest boosters that we can throw up. We did have the huge Saturn V, and when you took the S4B and emptied it, made a really nice volume. And the problem is that we actually ripped off this thermal shield on liftoff, and we also, when it left, it tore off the solar array on the side. But the big problem is this thing, you can note, is a solar inertial satellite. It doesn't tilt its solar arrays, and so this side faces the sun at all times. We got rid of that thermal shield, and boy, was that lab hot. Okay? So we had issues running Skylab. The Russians put on top of the Proton the biggest thing they could get there, which is about the size of a Winnebago, and they built it like a Winnebago, self-contained. It has everything you need to motor down the road and be a self-contained little home out in space. So they put on the solar cells and the thermal radiators and the aluminum skin and the thermal insulation and all the things that a little spacecraft like this has. They just made it bigger and put it on a big rocket. And they would live on that thing for a year, you know? That thing's the size of a Winnebago. Can you imagine crowding yourself in there that long? Can you imagine crowding yourself in here for more than about 2 hours? But they had to live there for a couple of days. Then they started making it more productive. They would go out by spacewalk and add on more solar arrays that could be delivered to the station. And they started anticipating those solar arrays, covering more and more with the thermal radiators. Finally, you got to where the entire spacecraft is covered with thermal radiators, trying to get rid of the heat that you're generating. And so you don't need much insulation. You're basically cooking the inside and pumping that heat out, getting rid of it on the night pass. And if you need more power and more cooling, then you launch another Winnebago and you rendezvous in the parking lot with it. So then they started figuring out that too many Winnebagos in a line is a problem. And so they said this is structurally hard to hold together until they figure out better materials and better docking mechanisms. So they started figuring out they couldn't go too far in any one direction, but if they spray out radially, they can go in many directions at once, which is what they did with Mir. In Mir, you can see these things that look just like the FGB. FGB stands for Funktionalny Gruzovoy Block, or Functional Cargo Block, standard spacecraft bus. Just like a Winnebago, 88% of everything gets delivered to space is the truck that carries it there. Same mass ratio on a Winnebago. So about 12-15% of this is the science payload that got to come up, and the rest is the truck, and it all gets glued together. Now look at the solar arrays starting to shadow each other. Look at the thermal radiators starting to cook each other. And you can see that this was an interesting large structure, but not the right way to build a spacecraft. So, it got to be a big dandelion puff, and it was 8 years ago today, 8 years ago tonight, that Mir was deorbited on March 23rd, 2001. And it went into the Pacific Ocean, roughly where we're thinking of putting International Space Station at some point after 2020. And it was about the size of a 3-story house, so you can see why we're kind of excited about the Transhab concept, the Bigelow concept, that is also the size of a 3-story house on a single launch. So inflatables can really help you there. But we and the Russians both realized and started working through the 80s on the idea that we would have to build our next spacecraft in space. That if you're going to get economy of scale beyond the launch, then you actually have to think about a launch dedicated to solar arrays, or a launch dedicated to just laboratory space. And so by the time you get the maximum sized rocket, we don't build skyscrapers out of the trucks that bring the materials there. We drop off the materials and we assemble it in place. So we had to consider putting the crew out there and using as much automation as we could to erect things. And we ended up realizing that spacewalking is really, really hard. And I think there's one going on right at the moment, isn't there? Yeah. So how's it going? Anybody know? Going good? Did we get the UCAS deployed?
No, they had issues.
Issues. As I said, spacewalking is hard. And so we pre-integrate as much as we possibly can. And so we have these big chunks, and we have these dedicated laboratories, and we deliver the utilities to them. But this all had to be carefully orchestrated, put together in space. That took a tremendous amount of spacewalking. But look at the scale of the pieces we get to put up. This is one of the backbone end plates of the truss structure. Look at the guy cleaning up the chips back here. And this is partially machined. This is one of those weight-saving things you get to do. You start with a big chunk of aluminum and cut away anything that isn't a space station. And that way, you don't have bolts and flanges and stuff in here. You just get great webs of thin aluminum. But you have to start with a massive block the size of this stage and then put it on a monster milling machine. All of those tools and techniques cost a lot of money. A space station, by the way, has over 540 facilities just in the United States dedicated to building, testing, training, and operating the space station. That's all the ground facilities, 540 buildings, specialized labs and stuff. And that's just the tip of the iceberg, because the Russians have built them, the Japanese have built them, the Europeans, the Canadians. We have sites all over the world supporting this one effort. The truss, you can see, turns into this monster thing just to support the utilities to serve the science on board. The Destiny Laboratory has more science aboard than the Mir did. It has more science aboard than Skylab did, combined. Right? And that's just one of the 3 major laboratories on the station. Spacewalking helped us put it together. And the problem is, how do you meet up there?